So last class, we looked at Taylor polynomials. In this class, we're going to investigate Taylor series. So Taylor polynomials have a stopping point, right? We would figure out the Taylor polynomial of degree 3 that approximates e to the 2x. So we did this out last class. So today we're going to look at Taylor series, where we let n, the degree of the Taylor polynomial, just go to infinity. So this was our formula for a Taylor polynomial, and we would stop at some point n. But instead of stopping, we're just going to write plus dot 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 and let it keep going forever. So for example, we're going to find the Taylor series, including the general term, for f of x equals e to the x at a equals 0. And Taylor series that are centered at 0 have a special name. They're called Maclaurin series. All right, so this table will help us organize our work. In order to plug into this formula for Taylor polynomials or Taylor series, we have to know f and a bunch of its derivatives. Right, so I'm going to take a bunch of derivatives. Then I'm going to plug in my a value into all those derivatives. Then I'm going to calculate my coefficients, which is f over a factorial, or f prime, a derivative over a factorial. And then my powers of a, my powers of x minus a. So in this case, a is 0. And then this is just x, because x minus 0 is just x. Okay, so I'm going to start by taking all my derivatives. So I start with f of x equals e to the x, which means f prime of x equals e to the x, right? Easiest derivative rule we have. F double prime of x is e to the x, etc. All my derivatives are going to be e to the x, which means when I plug 0 into all of these functions, I get 1. E to the 0 is 1. So f double prime of 0 is 1, etc. All my derivatives are going to be 1. So then my coefficients, looking at my formula for a Taylor polynomial, it takes f at the a value and divides by a factorial. So I already have the f of a values done. They're all 1s, and I just need to put them over the appropriate factorials. So my first coefficient is going to be over 0 factorial. So I have 1 over 0 factorial, then 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, etc. And then my powers of x minus a, I'm just going to start with 0, and my a value is 0, so this is just going to be x to the 0, x to the first, x squared, x cubed. And then I'll plug it all into the formula for the Taylor series. So I've got my coefficients and my powers of x. So what is 1 over 0 factorial? We'll just simplify a couple of these. 1, that's 1 over 1, which is 1. This is 1 over 1, which is 1. I'll leave the others with the factorial in them. So e to the x is going to be, coefficient is 1, x to the 0. So 1 x to the 0. My next coefficient is 1, and then multiply by x to the first. My next coefficient is 1 over 2 factorial times x squared. And then my next coefficient is 1 over 3 factorial, and you multiply by x cubed. Do one more. 1 over 4 factorial times x to the fourth. And then you just write plus dot dot dot. Keep writing these terms in this format. So if I wanted to write this in closed form in sigma notation, every term looks like, let's start at 0 because I have x to the 0 as my first term. So I'm going to start at n equals 0. And every term looks like x to the n. I've got an exponent of 0, then 1, then 2, then 3. So x to the n. And then I'm dividing by n factorial. that good? Okay, so to find the interval of convergence, this is practice from a couple of classes ago. To find the interval of convergence for a power series, we always use the ratio test, which says look at the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. Okay, so my n plus first term means replace every n in the general formula term with an n plus 1. So I have x to the n plus 1 over n plus 1 factorial divided by the nth term, which is x to the n over n factorial. Okay, so this is x to the n plus 1 over n plus 1 factorial, and flip and multiply. So I have n factorial over x to the n. Okay, x to the n plus 1 over x to the n. Those are like bases, so you subtract the exponents and you're left with x to the first. Does it live in the numerator or the denominator? Numerator. And then I have n factorial over n plus 1 factorial. So this is n plus 1 factorial is n plus 1 times n minus 1 down all the way down to 1. And this is n times n minus 1 all the way down to 1. So that reduces to 1 over n plus 1. The x has nothing to do with the limit. The limit is involving n, not x. So I can take the x outside the limit. It becomes the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. What is that limit? 0, which is 0. So what do we look for with the ratio test? What was I hoping that limit would come out to? Something less than 1. When that limit is something less than 1, we get convergence. So it turns out that it does not matter what x is. You always get a limit less than 1. It'll always be 0. So that means that my interval of convergence is negative infinity to infinity. Or you could write it negative infinity is less than x is less than infinity. Converges no matter what the value of x is. Okay, so we're just going to do this whole process a second time, practicing finding a Taylor series. This time I'm going to find the Taylor series for f of x equals the ln of 1 plus x near a equals 0. We're going to write out the terms up to degree 5, and then we'll write plus dot dot dot. And we're not going to put the final answer into sigma notation like we normally would, because that's the first part of your group activities. All right, so if I need to write out up to degree 5 terms in the Taylor series, then I need 5 derivatives. So I'm going to start with f of x, and I need f prime, f double prime, f triple prime, and the 4th derivative, and the 5th derivative. Okay, so f of x is the ln of 1 plus x. So that's where we start. Now I have to take 5 derivatives. So the derivative of the ln of some stuff is 1 over the stuff times the derivative of the stuff. But the derivative of 1 plus x is 1. So I'm not going to bother writing it down. And just for the purpose of making the next derivative easier, I'm going to rewrite this as 1 plus x to the negative 1. So to take the derivative of 1 plus x to the negative 1, I'm just going to use the power rule. That's some stuff to the negative 1. So I bring the negative 1 down in front, copy the stuff, reduce the exponent by 1. Normally, I'd multiply by the derivative of the stuff, but the derivative of the stuff is 1 in this case. So I won't bother writing it down. I normally wouldn't bother writing it down. I just did just to remind you of the chain rule. Okay, so now this is just the power rule over and over again. So I'm going to bring the negative 2 down. Negative 2 times negative 1 is 2. Copy the stuff, reduce the exponent by 1. Negative 3 times 2 is negative 6 times 1 plus x to the negative 4. Bring down the negative 4 and you get 24 times 1 plus x to the negative 5. Okay, so I have 5 derivatives. Now I have to plug in the value I'm interested in. They said that value is a equals 0. So I'm going to plug 0 into each of these. So the ln of 1 plus 0, the ln of 1 is 0. Good. If you didn't know that, that's what calculators are for. And then f prime of 0, that's 1 plus 0 to the negative 1. 1 to the negative 1 is 1. And f double prime. So 1 to the negative 2 is 1, but then there's a negative out front, so this becomes negative 1. One to the anything is 1, times 2 is 2. Fourth derivative at 0, 1 to the anything is 1 times negative 6. And the fifth derivative at 0 is 24. Okay, so then my coefficients are the f values over factorials, right? So it's going to be this f value over the appropriate factorial. 0 factorial, then 1 factorial, then 2 factorial, then 3 factorial, 4 factorial, and 5 factorial. And then my powers of x minus a is 0, so this is just x to the 0, x to the first, x squared. And I might simplify these. 0 over 0 factorial, that's 0 over 1, which is 0. Oops, that's supposed to be 1 over 1 factorial. 1 over 1 factorial is 1. I'll leave the rest. Actually, no, I'm going to simplify all of them. 2 factorial is 2, so this is negative a half. 3 factorial is 6. 2 over 6 is a third. 4 factorial is 24. Negative 6 over 24 is negative 1/4. And 24 over 5 factorial, 5 factorial is 120. And 24 over 120 is 1/5. So maybe you see a pattern in the coefficients. 1, a half, a third, a fourth, a fifth, and the signs are alternating. So now I'm going to plug it all into the Taylor series formula. So f of x, which is the ln of 1 plus x, is equal to, I'm not writing approximately because I'm doing an infinite series. If you chop it at any point, it's approximately equal to the polynomial, but I'm going to put the dot, 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 making it equal to. So I have my coefficients times my values of x. So my first coefficient was 0, so I wouldn't normally write it down, but I'll just put it there. Then I have 1x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th plus 1/5 x to the 5th minus, keep going like that. So those coefficients are reminding me of something. It's the harmonic series, right? The alternating harmonic series. Just the coefficients. If you ignore the x's, you have 1, a half, a third, a fourth. That's the harmonic series, and it's alternating. So we know it converges. We know the alternating harmonic series converges by the alternating series test. Using this Taylor series, I actually can figure out what it converges to, right? So if I replace all of the x's in this formula with a 1, I would get the alternating harmonic series. So let's just say f of 1, it's the ln of 1 plus 1, or it's the same thing as if you plug a 1 in for all the x's in the series, in the Taylor series. So we would have 1 minus a half plus a third minus a fourth plus 1/5 minus forever, that entire series. So we now know that that infinite series, aside from the fact that it converges, we already knew that. Now we know when you add those all up, you get the ln of 2. I think that's a little surprising. You're adding up an infinite number of rational numbers and getting an irrational number. That is weird. So what are Taylor series useful for? They are how a calculator finds values of trig and log functions. So when you type ln of 2 into your calculator, it gets an approximation by using a Taylor series. They can help us calculate sums of series. For example, the alternating harmonic series, or the sum of 1 over n factorial, which adds up to e. Like, that's surprising too. They can help us understand new functions. We're going to talk about e to the I theta next class. And they can help us estimate derivatives or integrals. We'll do a little bit of that today, more on it next class. Okay, you try some.